In the last two segments of this lecture, what we're going to do is we're going to consider the topic of non-circular geometry pipe flow. And when we're dealing with non-circular geometry, one of the things that we have to do is determine what diameter we should be using for our analysis. And what we tend to do with non-circular geometries is we use what is referred to as being the hydraulic diameter. Now, the definition of the hydraulic diameter, first of all, it has the symbol capital DH. It is 4 times the cross-sectional area divided by the perimeter. So with that, let's take a look at a couple of common shapes that we may encounter dealing with this. Okay, so there we have 2 different cross sections for a pipe. One a traditional round pipe, and then the other one a square pipe. And so, recall we said the hydraulic diameter was 4 times the cross-sectional area divided by the wetted perimeter. So for the round shape, the area we know is pi r squared, and the perimeter is 2 pi r. And consequently, evaluating the hydraulic diameter, what we end up with is the hydraulic diameter for the round shape is just 2 times the radius, which would be the normal diameter. Now looking at our square cross section, we end up with just directly the one of the dimensions of the square cross section. So those are ways that you can calculate the hydraulic diameter, and this is what you would use for the length scale when you're calculating the convective heat transfer coefficient dealing with non-circular geometry. Now for laminar flow, fully developed laminar flow, there are tables that exist that will show values of the Nusselt number as well as a pressure drop characteristic for different types of shapes, so different aspect ratios, triangular cross sections, all kinds of different things. If you look in any heat transfer textbook, you'll probably find a table with these values in it. And typically what they will plot is they will have a Nusselt number, and there will be Nusselt number with subscript h, and that usually denotes constant axial heat flux. And Nusselt number with T, and that would be constant axial wall temperature. And if you recall, those are the 2 boundary conditions that we used when we were determining the bulk temperature within a round pipe flow. And other things that they may have a thing with the friction factor multiplied by the Reynolds number, and the Reynolds number is evaluated using the hydraulic diameter. So those would provide us with information about the convective heat transfer coefficient would be embedded in the Nusselt number, and the friction factor, the pressure drop, would be in the friction factor Reynolds number. And in both of the non-dimensional numbers, Nusselt and Reynolds, the length scale we evaluate they're evaluated based on using the hydraulic diameter DH. So that is how you handle cases of non-circular geometry. What we're going to do in the next segment is we're going to solve an example problem that involves a non-circular geometry system, and we will compute the heat transfer for that type of geometry.